Thanks for tuning in to First Principles Daily, episode 12 for June 17th, 2026. Today, an industry whose idiot index is begging to be attacked. Rockets, once priced at roughly $10,000 per kilogram to orbit, now reach a few thousand through reuse, because the question changed from building expendables cheaper to whether the hardware must be thrown away after one flight. For most of the space age, a Falcon 9 class booster would have been discarded after a single flight. Its tanks, engines, and avionics would have been committed to the ocean with no thought of recovery. Today, the same booster returns, lands, and flies again, sometimes more than a dozen times. That change turns the dominant cost item from fabrication into inspection and refurbishment. The shift did not come from asking how to make each new rocket slightly less expensive. It came from asking what physics actually demands must be replaced after every launch and what can be retained. Launch providers inherited a pattern set by the first ICBM-derived vehicles. The rocket existed only to deliver its payload. After that, the structure had served its purpose and was abandoned. That convention spread because each national program copied the approach that had already worked. Then they optimized within it by shaving a few percent off tank fabrication or engine assembly. The result was a mature industry in which every kilogram delivered to low Earth orbit carried an amortized cost on the order of $10,000 or more. That cost was driven almost entirely by the fact that the vehicle itself was written off after one use. No one inside the established firms treated the expendability as a variable. It was simply the way rockets were built. Consequently, the cost per kilogram moved only when governments funded larger vehicles or accepted lower flight rates. It never moved because the hardware itself was asked to do more work. The underlying assumption remained that the energy and materials invested in a booster were single-use by nature. An assumption no one revisited because the analogy of a missile that flies once had become the entire frame. SpaceX began by separating the requirement of reaching orbit from the requirement of building a new rocket for every mission. The physics floor is set by the energy needed to accelerate roughly 20 tons of payload. It is also set by the structural mass needed to contain several hundred tons of propellant. That energy and that mass do not inherently disappear after one flight. A rough magic wand estimate for the materials in a Falcon 9 first stage sits in the low hundreds of thousands of dollars at commodity prices. Those materials include aluminum lithium tanks, Merlin engines, avionics, wiring, and thermal protection. By contrast, the completed stage under the old expendable model carried an effective cost measured in the millions. That ratio already pointed to an idiot index well above 10 before reuse was even attempted. To see why, compare the two figures directly. If the raw materials cost a few $100,000 and the finished expendable stage cost several million, the multiplier lands comfortably above 10. That gap signals that design and process choices, not the atoms themselves, are driving most of the price. The first concrete move was therefore to retain the stage rather than discard it. Retention required proving that the tanks and engines could survive re-entry heating, aerodynamic loads, and landing impact. Once survival was shown, attention turned to lowering the cost of returning the stage to flight condition. Propellant manifolds were redesigned so fewer separate lines and joints were needed. That change removed potential leak paths and inspection hours. Grid fins and landing legs were added as reusable elements. Their mass penalty was accepted because it eliminated the need to build an entirely new attitude control and recovery system for each flight. Engine restart sequences were simplified by changing valve timing logic rather than adding hardware. That cut both part count and the number of pre-flight checks. Over successive versions, the turbopump assemblies moved from multiple machine forgings to configurations that combined several functions into single cast or additively manufactured housings. Each consolidation removed mass, seals, and assembly labor, because each of these steps attacked the refurbishment cost directly. The marginal expense of a second flight fell far below the cost of building a fresh stage. That movement lowered the effective idiot index even though the raw material floor itself had not changed. Falcon 9 flights now achieve costs per kilogram to low Earth orbit reported in the low thousands of dollars when averaged across many reuses. That marks a clear reduction from the prior industry baseline, yet the figure remains well above the theoretical material floor. The current refurbishment process keeps the idiot index of a reused booster perhaps 3 to 5 times the magic wand materials estimate. That stands in contrast to the double-digit figure of a purely expendable design. Limits remain visible because the engines still require post-flight work that cannot yet be eliminated by design alone. The fairing recovery system, while demonstrated, adds its own inspection overhead. The approach also trades some payload performance for the propellant margin needed to return the booster. That explicit compromise was accepted because the reduction in amortized hardware cost outweighs the lost mass. Further gains will require either dramatically cheaper inspection methods or a booster architecture whose engines and tanks need essentially no refurbishment between flights. A vehicle whose price greatly exceeds its contained materials is signaling that the design or the operational concept, not the physics, is carrying the cost. The signal appears whenever the finished item costs many times more than the raw materials inside it. In the case of an expendable booster, the multiplier sat well above 10 because the entire stage was treated as single use. Questioning whether the entire rocket must be replaced after one mission opened a lever that incremental improvements inside the expendable frame could never reach. The separation began with a simple distinction. Reaching orbit is a physics requirement. Building a new rocket for every mission is an inherited assumption. Once those two ideas were pulled apart, every subsequent redesign could target the refurbishment cost instead of the fabrication cost. The same pattern of separating physics requirements from inherited assumptions now sits ready for any hardware that is built once and discarded. Consider a pressure vessel, an aircraft fuselage section, or a high-value industrial pump. Each carries an idiot index set by how many times its materials are asked to perform before they are thrown away. When that index stays high, the opportunity lies not in cheaper raw stock, but in rethinking whether replacement is required at all. The Falcon 9 example shows that proving survival and then simplifying return to flight steps can compress the index dramatically. The same sequence can be applied wherever a product is currently designed around a single cycle of use. What would change first if the next generation of launch stages were designed from the outset around repeated flight rather than around a single use? That's First Principles Daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it, and subscribe wherever you listen. I'm Patrick in Vancouver. One example or one opportunity every day. See you tomorrow, and if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove